Hello everyone, thanks for the introduction. I'm showing my presentation today about classifying patients with severe chronic disorders of consciousness using multislice modularity of brain networks from fMRI data. A quick outline. So first I'm going to tell you what patients with severe chronic disorders of consciousness are. Then I give the key ideas. Then I plan to talk about multislice modularity, but I will do this very quick since we heard it in the last talk. Then I'll give the results and a conclusion and an outlook. So first of all, the patient group. The patients with severe chronic disorders of consciousness are patients that are in some kind of comatose state. The coma is the first state. This is the acute state right after the injury or after the disease. These are patients that are not responsive and not aware of themselves nor the environment. The next are the unresponsive wakefulness syndrome patients, which is also called the apallic syndrome, coma vigile, or vegetative state. These are patients that have a day and night cycle. That means that they spontaneously open the eyes and close the eyes, but they're not aware of themselves nor the environment. The next are minimal conscious state patients that are sometimes aware of themselves nor the environment, but we are not really sure about that. But they at least show signs of awareness. This is a very heterogeneous group. That's why it's subdivided in MCS plus and MCS minus. Then we have the locked-in syndrome. The locked-in syndrome is not a disorder of consciousness, but it's often misdiagnosed because the patients cannot move. So there's the complete, incomplete, and the classic locked-in syndrome. It depends on which part of the body you can move as a patient, then you're classified to one of those. And the last one is the locked-in plus syndrome. The locked-in plus syndrome is a combination of a locked-in syndrome and then UWS or MCS. Yeah, why did we look at this patient group? We did this because the diagnosis is a huge problem in this patient group. In general, there's behavioral testing is used, but the question is, should this be the golden standard? And the answer is probably not, because we have a misdiagnosis rate of 43%. Which is very devastating for the patient when you think you're diagnosed as not being aware of yourself and the environment, and in reality you know and see and hear everything. So we need additional tools, and functional magnetic resonance imaging seems to be a very promising tool for this diagnosis and prognosis. So the key ideas of my research. So we use resting state networks from fMRI for the diagnosis, which also has an impact on the prognosis of this patient. So we use resting state networks because it's the easiest to collect, and especially in this patient group, it's super hard because you don't know whether they cannot do it or they just don't want to do it. So it's hard to use a task. That's why we focused on resting state. From the resting state network, we built graphs with the regions of interest nodes and the temporal correlation of edges. And then we try to find new classification methods using the multislice modularity from MUCA. So here in the bottom you see a graph, and as you've heard before, graphs can be subdivided in modules, and a module is some kind of region that is more interconnected between each other than to the rest of the network. And here you see like every color is a module in this graph. Here's a picture of the multislice modularity, which we have also seen before. Like every slice is, in our example, one subject. Most often it's used that one subject is looked over in the evolution of time, but we don't do this. We use the categorical ansatz, and the categorical ansatz describes that you connect every node to each other, not just in a sequence, not just in a row like at time point 1, time point 2, time point 3, but you have that the whole slices are connected, so slice 1 is also connected to slice 3, and slice 1 to slice 4, and every node to itself in each other slice. So this is what we use because we think when we use this that we get a better average subject in general, and this is what we want to do. So here's the overview of our workflow. We start with Fisher's set correlation matrices. We did this for each subgroup, so we had healthy controls, an UWS group, and an MCS group. So we did this 3 times. So we used the Fisher's set correlation matrices with thresholded with theta of 0.1, which means we just use the 10% of strongest connections, and then we binarize the whole system to get the adjacency matrix. Then we connected this with the omega, with the interslice connector, and calculated with the Gann-Levin that we heard before, the modularity matrix, so the modularity partitions. And it is a heuristic method, so we did this 100 times to get 100 different modularity matrix, entries of the modularity matrix. From this modularity matrix, we can calculate the agreement matrix, and an agreement matrix gives more or less the probability that node I and node J are in the same module. So let's turn to the results. First, we can compare the agreement matrices. So we have one agreement matrix for each group, one for the healthy controls, one for the UWS, and one for the MCS patients. And when we compare like the UWS or MCS patients to our healthy controls, we find a lot, a lot of different ROI assignments. This just means that the brain structures are very different. This was to be expected because like being in coma is a very severe disease or illness. And comparing now the UWS and the MCS patients, we find that 9 ROIs have different module assignments. So we have 7 ROI pairs. This means the most important part is the middle temporal gyrus posterior division right, because this one region and the parietal operculum cortex left, the central operculum cortex left, the frontal operculum cortex left, the insular cortex left and right, as well as the Henschel's gyrus, were significantly less often in the same module when comparing MCS and UWS patients. And we have 2 regions, namely the planum polare right and the temporal pole left, which were more often in the same module. So these are our results from the comparison of the agreement matrix, but we wanted to go a step further and see whether we can do a classification with that. And we did it like this. So we had the agreement matrix for each of our groups. So we had 3 agreement matrices, and we get 1 new subject and want to classify the subject. So we started by calculating a consensus vector. A consensus vector is like a representation of what the agreement tells you a partition would look like. And so we calculated the consensus vector for UWS, a consensus vector for MCS, and 1 consensus vector for healthy controls. Then we took the new subject, also calculated a consensus vector, and had then partitions for each. Like in the consensus vector, there's this partition with the highest probability, or some kind of also a heuristic. But you can compare the consensus vectors afterwards. And we did this via partition distance. And the partition distance, we did like UWS to the new subject, MCS to the new subject, and healthy control to the new subject. And then we checked which partition distance was the closest, and the closest was classified the new subject. So when we see our confusion matrices in the bottom, the bigger one with the UWS, MCS, and healthy controls shows the result when we use all 132 ROIs in our system. And we see that actually the confusion masses don't look that bad at first sight, but when we have a closer look, we see that this good separation is just between patients and healthy controls. And this is in general not the problem in the clinic, because in general you can say whether someone is healthy or whether someone is in some kind of comatose state. But the problem is more to distinguish UWS patients and MCS patients. And so we focused just on this separation. I don't have the confusion matrix right now, but I can tell you that it looks very bad. So the classification is just random. So what did we want to do? We wanted to improve this, and so we shortened our consensus vector and just used the 9 ROIs that are most important in the modularity comparison from the agreement matrix. So we had the consensus vector just consisting of our 9 ROIs and compared those to each other, and we find this new confusion matrix, which now doesn't look that bad. So we have conclusion and outlook. So our first conclusion is, of course, that the algorithm works for severe chronic disorders of conscious patients, And we find a classification that 62.07% of the UWS and 70% of the NCS patients were classified correctly. It doesn't look that good at the first sight, but when you compare it to the behavioral testing, that 43% is even misdiagnosed, the result is not that bad. But we want to improve it, of course. But we need more patients to get an even better classification. But it's very hard to get these patients, and a bigger cohort just needs time, so we are waiting for the patients to come in to scan them. And we also have the bias from the inaccurate behavioral testing in the model, because we needed some ground truth. Of course, our physicians did the best to classify the patients correctly, but we cannot deny this point. So we also want to do in the future, like doing follow-ups and see whether the patients can recover from their state or not, and include this as the ground truth then. And the last 2 points is also outlook. What we want to do in the future is also look in the classification via locked-in syndrome, locked-in plus syndrome, NCS plus and NCS minus. But since these are all subgroups, it's very hard to get a huge enough cohort to even say something. So we also want to test it with other neurological disease and see whether our method is worth going on. Well, last but not least, I want to thank all my collaborators and all the centers that participated.